Today, we'll learn about Sytrus.
Sytrus has 6 customizable oscillators or operators with FM, frequency modulation, RM, ring modulation or amplitude modulation, subtractive and additive synthesis options, making it an all-round synthesis powerhouse. We will talk about these 3 synthesis methods and how Sytrus can take advantage of them. It also includes 3 filter modules with per voice wave shapers, an effects module with chorus, 3 delay lines, and unique per voice programmable Unison settings. Sytrus has 6 operators with lots of settings that can be routed either directly out of the plugin with these knobs, into the chorus, reverb and delay effects here, into one of the 3 filters here. These need to be routed to the output as well to make any sound, or to any other operators using the FM or RM matrix here. You can also chain the filters via the next control. More on that in the Love Filter video. Be aware that the stereo panning controls here and the panning envelope, more on envelopes later, only apply when an operator is directly routed to the synth's output, as the filters are per voice, so each note in a chord gets its own instance of all filters, and therefore they have to be inserted pre-panning. They also each have their own panning control. Every operator has a set of 6 sliders to pre-calculate the waveform. It's possible to make all basic waveforms with these sliders. By default, the first slider moves gradually between sine wave at the bottom, triangle at 25%, saw at 50%, square at 75%, and short pulse at 100%. The next 4 sliders to the right are used to modify this wave shape. Tension, skew and sine shaping do what you would expect. The pre-filter acts like a low-pass filter on the waveform. And noise adds white noise into the oscillator signal. The 3 switches below the waveform display constrain the waveform in different ways. The half switch is used to squish the waveform into the top half of the display. This means it does not oscillate onto the 0 crossing point. All negative amplitude values are gone. The even switch compresses the waveform into the left or right half of the display and adds silence in the other half. And finally, the absolute switch, I like to call this the mirror switch, will mirror the waveform in the vertical center. Use center to remove any DC offset, that is, a vertical offset in the waveform. For example, the half switch will pretty much guarantee that there is DC offset in the output. D-click can remove initial clicks on note start. Band limit can limit the frequency response of oscillators to within 20 kHz to avoid aliasing. This is a very efficient but lossy process, so it can be helpful when oversampling is using too much CPU. This is most easily demonstrated with slide notes. Pluck behaves similarly to its counterpart in Hammer, only here it's controlled via the damping envelope. You'll notice that my FM matrix just deactivated the FM controls in operator 1's row. An operator using this control cannot receive FM from another. It can still be used as an FM source though. You can set the oscillator's starting phase here, check global to have it free running, adjust operator volume, which also controls FM amount but not RM amount, and choose how much the pitch envelope affects the pitch here. The 2 boxes here determine the main pitch of the oscillator. The left one is a static value in hertz. When the right one is set to 0, this is exactly the fundamental frequency you will get for every note you play. When the right one is higher than 0, the left one is a pitch offset. The right box, however, shows pitch ratio. Every whole number represents a step in the harmonic series or Fourier series. More on that later. For now, know that octaves are powers of 2. So ratio 1 is 2 to the power of 0, ratio 2 is 2 to the power of 1, and ratio 4 is 2 to the power of 2, and so on. Of course, you can click and drag up and down to the right of the decimal point and make fine adjustments. This articulator section should be familiar to you if you've watched our Love Filter or SliceX videos. Basically, the top row of tabs is for parameters that can be modulated, and the bottom row is for articulators modulating those parameters. Panning, volume, FM or RM amount, pitch, phase and damping can be controlled by envelopes. See the card on screen right now for a deeper explanation on those. LFOs, key tracking, velocity tracking, mod X and Y macros, these are on the main tab, random mapping and Unison offset mapping. We will talk about the oscillator tab later on. The filters have slightly different parameters for modulation. However, since they are largely the same as Love Filter's controls, you can click the timestamped card on screen right now to get up to speed on how they work. To understand the intricate controls in the FM matrix and articulator settings, let's go over the 3 synthesis types Sytrus can perform. Subtractive synthesis is the concept of designing a sound via removing frequencies from or attenuating frequencies in a harmonically complex starting sound. Any basic waveform is made up of individual sine waves at frequencies along the harmonic series or Fourier series. If you want the mathematical proof behind that, there is a great video by 3Blue1Brown explaining how individual sine waves or partials make up a complex waveform. The harmonic series starts with the fundamental frequency and then keeps incrementing the frequency by the fundamental frequency for every extra step along the series. So when our fundamental is A equals 440 Hz, and we want to know the frequency of the third order harmonic, we add 440 Hz to get to the second order harmonic, and then again 440 Hz for the third order harmonic. This is precisely an octave and a perfect fifth above the fundamental, or a 3:1 ratio. The more of these harmonics you add, the more complex your waveform will be. So then, for a synthesis type that works by taking things away from a complex source, you would probably want to start with the harmonically richest waveforms, like a saw wave. A saw wave has each and all of the harmonics in the Fourier series present, so it is by definition the most complex of the basic waveforms, which is why most subtractive synthesis examples start from a saw wave of some kind. One of the most prominent examples of this is the supersaw. It's a very recognizable synth sound used in pretty much every music style to some extent, to play chords or pads. The principle is, we've got a bunch of saw waves that are slightly detuned going into a filter, and the filter is moving. Another example is an acid bass sound, made popular in the early 90s and still used across many dance genres all over the world. We have a plugin dedicated to those, Transistor Bass, where this requires no setup at all, but you can get similar from Sytrus if you set it right. It's almost like a supersaw, but you'll only need to use one saw wave to do it, and you'll have to be very meticulous about the filter frequency and resonance. Dial in the wave shaper for some distortion and you're good to go. And probably even more popular than the supersaw is the Reese bass. It's made its way into dance music first and then was adopted by pop music and hasn't left since. It's a sound consisting of 2 detuned complex waveforms phase cancelling each other out, then using a filter and some type of distortion. Can be aggressive, or subtle. noted earlier, all complex waveforms can be broken down into individual sine wave partials. So can you then also add many sine wave tones in a harmonic series together and create a complex waveform from them? Oh boy, can you ever!
While Sytrus's additive synthesis capabilities are not as advanced as what you get in Harmless or Hammer, they are not to be underestimated.
For example, the harmonic editor in the oscillator tab, told you would get to this, lets you create up to 128 copies of the currently active waveform shape at all of the first 128 harmonic series positions, and control their individual phases. You can do this per operator, meaning you get 6 of these additive engines to play with. This is particularly useful with the pluck option and using the damping envelope, which functions a bit like the pluck function in Hammer. It sounds like a low-pass filter, but it is actually gradually turning off higher harmonics rather than filtering. Great for keyboard and electric piano sounds. Did you know that Sytrus can resynthesize single-cycle waveforms with its additive engine? Grab a single cycle with a timbre you like, and drag and drop it onto Sytrus's waveform display to get a resynthesized version that you can edit further. FM, or frequency modulation synthesis, is the process of modulating the pitch of a so-called carrier signal, which is typically a basic waveform, with another signal, called the modulator, at audio rate. That means at least the modulator frequency should be between 20 and 20,000 Hz. That is rather quick for modulation. Think of it like an LFO or low-frequency oscillator modulating pitch, like a vibrato for example. Only the frequency really isn't all that low, and as a result, you don't hear a warbling, pitchy, modulated signal, but instead the result is much more like a new, more complex waveform. Most digital FM synthesizers, Sytrus included, do not in fact modulate pitch with the modulator signal, but phase instead. A gradual adjustment of a waveform's phase results in a pitch change just as well. This was done because when digital FM synthesis first arose in the early 1980s, computer technology was not quite advanced enough to modulate pitch at audio rate in the digital domain. Plus, through testing with analog components instead, it was determined that the sound of phase modulation was more useful in a musical context. As with direct pitch modulation, the harmonic qualities of the resulting audio signal were often lost, and the resulting pitch was too unpredictable. With phase modulation, you can be sure that the modulated resulting waveform will always oscillate at the lower of the two pitches, unless one of the two pitches is so low it is no longer audible on its own. Both phase and frequency modulation produce a result based on how a few basic attributes of the modulator are changing: amplitude and frequency. When the amplitude of the modulator is increased, the strength of the modulation is also increased. The strength refers to the difference between the highest and lowest pitch in the result. Think of a subtle tiny vibrato versus an exaggerated big vibrato. For FM and PM in the context of synthesis, the frequency of the modulator is usually higher and an audible alternation of pitches is lost, and instead an entirely new timbre is created. For phase modulation, the frequency of the modulator also affects the modulation strength. Sytrus FM matrix has rows for operators receiving modulation. Logically, that means the columns are for sending modulation. If I turn this knob up, I'm sending operator 1 into itself. This is called feedback modulation, and it makes saw wave-like sounds out of sine waves. If I Alt-click to reset, or right-click to mute, and turn this knob up instead, I am sending operator 6 to modulate operator 2. Here's what that sounds like. Let's now turn the output of 2 back down and turn this knob to the left, inverting 2's polarity for modulation, and listen to operator 1. Since 6 is still modulating 2 and 2 is modulating 1, by the time 2 modulates 1, it has already been modulated by 6, and we get a more intense modulation result despite the other operator settings being the same. Let's mute 6 modulating 2 and compare. When you modulate a sine wave carrier with a sine wave modulator at a multiple of 2 times its frequency, you will get only odd-numbered harmonics. So it will sound like it's related to a square wave. In turn, modulating with odd-numbered harmonic steps, including 1, will excite the carrier's harmonic series at the pitch of the modulator, so the result has even and odd-numbered harmonics. The main difference between phase and frequency modulation is how the pitch of the result responds to the modulator's shape. With frequency modulation, the pitch responds directly to the modulator waveform, and phase modulation creates pitch movements that are the mathematical derivative or slope of the modulator waveform. This means that for frequency modulation, the pitch of the result is at its highest when the amplitude of the modulator is also at its highest. For phase modulation, the same thing happens when the slope is at its maximum value, which for a sine would be at the zero crossing, going from negative to positive. For the lowest resulting pitch, frequency modulation simply follows the actual value of the modulator again. For phase modulation, it occurs at the zero crossing to the other direction, from positive to negative. So, what does that mean in reality? You can modulate a basic sine wave with a very low frequency waveform to find out. Let's choose a sine wave as the modulator first. I will route operator 2 to modulate operator 1, like so. Let's set the frequency to something very low. Perfect. Hold on. This looks like it's moving like a sine wave would. Did I say the wrong thing? Speeds up, slows down, like a sine wave. No, in fact, the slope of a sine wave is a cosine, a sine that is 90 degrees out of phase, so this is expected. Let's change the modulator to a triangle. Here we can see the full effect of this. A triangle's slope is essentially 2 interchanging static values, so a square wave. We can see clearly that there are 2 distinct pitches being played. Interesting to note too is that the more I raise the modulator pitch, the further these 2 pitches drift away from each other, until the lower one hits 0 Hz and flips back around. So the higher the pitch of the modulator, the more it affects the resulting audio. This is because frequency can affect the slopes of the modulator in an identical way to amplitude. A higher frequency waveform will have steeper slopes, just like a higher amplitude waveform will also have steeper slopes. Authentic frequency modulation doesn't care about the slope, but when using phase modulation to achieve FM, modulator frequency will also affect modulation strength together with amplitude. So how can you use this knowledge to create great sounds? A classic FM sound that is fairly easy to make is a pluck with a carrier at ratio 1 and the modulator at ratio 2. This type of FM pluck is often called an onomatopoeia for what it sounds like. Donk. Just create a downward sloped envelope in the mod tab and there we go. That's it, you variate from here. When FM synthesis first rolled around, pop music was full of these driving, gritty synth basses that have recently made a resurgence in synthwave music. This is the quintessential sound of FM synthesis. We haven't talked about ring modulation or RM yet. It works in a similar way to FM, but instead of phase or pitch, the modulator will affect the carrier's level. The carrier's level will be multiplied with the modulator's level. So let's go back to our slow example patch, but this time let's use the RM matrix. As you can see in the scope, whenever the modulator's wave is in the top half of the display, the level response is positive polarity, and when it's in the lower half, the level response in negative polarity. So it's like a really quick bipolar volume automation. The same sonic rules that apply for FM apply here. Even numbered modulation ratios generate only odd harmonics, and odd numbered ratios will generate the full series starting at modulator pitch. We can also make it so the modulator doesn't change the polarity of the output. This is where the half button comes in. Since the modulator now only oscillates from 0 to +1 and no longer has any activity from -1 to 0, the modulated signal stays in the same polarity. This process is called AM, or amplitude modulation. This is like a really quick unipolar volume automation. This process makes sense to use for adding white noise to bass sounds, for example. Take a basic waveform, modulate a white noise operator with an AM shape, and add them together. Immediate noise base. Set the phase and shape of the AM operator to best suit the underlying sound. Equipped with all this knowledge, we can now revisit the concept of the respace, but supercharge it a little. Use AM to simulate the rhythmic phase cancellation of the respace without detuning the actual core sound. This technique is rather advanced, but produces very intricate and precise results, as you can adjust the frequency of the oscillation via the AM operator's pitch. An AM modulated operator will also apply this rhythm to the FM when it's used as a modulator in the FM matrix. This allows precise control of key-tracked FM and AM motion via one operator. Very handy for restyle bass sounds.
And with that, we've reached the end of this tutorial.